All right, so KSP is just a extension of equilibrium. So when you see these problems, it's kind of just going to be a reminder today, because you already know how to make ice charts, you already know how to solve for K values, but KSP is specifically for dissolving a solid. So you're always going to write your reaction with the solid going to the ions. So far you've learned Kc, Kp, Kq. Now we're going to do KSP, and then when we get to acids and bases, we're going to do Ka and Kb, and they always are the same. It's just products over reactants, and then you're solving for the concentrations or the pressures. All right, so this is the KEQ, which is KSP, for a solid dissolving in water. You always start with the solid, you always make your ions. The KSP expression here is the concentration of the ions divided by the reactant. But why can't I include the reactant concentration? Because it's a solid. So you always do products over reactants, and we always evaluate that. But you can't have any solids and no liquids. So by default, our KSP expression is always just going to be is equal to the concentration of the products, which will always be your aqueous ions. So you can have numbers that are less than 1 for sure, but if you have a number that's less than 1, that should tell you that that just means that you have very, very few ions floating around in solution. So sometimes we say things don't dissolve at all, right? Like you throw something and it doesn't dissolve in water. That's not necessarily true because everything has an equilibrium constant. It's just that some of the ions, like the second you drop it in, it produces 2 ions, say, and then that's it. It can't hold any more, so now we just say that it's not soluble. But everything has a KSP value. So it's showing you here that your KSP values can go from 1 times 10 to the negative third all the way to 1 times 10 to the negative 54th. That's a really small value. It just means that it doesn't dissolve really at all. So just as a side note here, remember that when you have a coefficient in the front, this becomes your exponent for your expression. So don't forget to include the exponents from the coefficient. Remember that? Okay, so your concentrations, you're going to either calculate them or they'll give them to you. And we're going to, instead of, when we use equilibrium, we put x. So we would say this is x, 2x, and then we would come up with like a 4x cubed value. Do you remember all that? For solubility, when we use KSP, instead of using x, I'm just telling you, we use s throughout the entire thing. You could use x, but s is solubility, so that's why we say s. All right, which compound is least soluble in water at 298? So the important thing is that you recognize that everything has a different solubility in a different solvent at a different temperature. So this is specifically for water at 298. So you have calcium carbonate and you have lead 2 chloride. Which one is more soluble, least soluble in water? So don't call out, just let everybody think. This is my KSP value. These are my concentrations of ions that could be in there. So which one? Henry?
Calcium carbonate.
So calcium carbonate has a lower KSP value, which means that it has fewer ions in the solution, which means it's less soluble, right? The more ions you have, the more soluble something is. So if you have a low KSP, that means low ions. And this has higher amount of ions. Okay. Solubility, we know, is the maximum molar concentration of formula units that will dissolve at a given temperature. Formula units, what does that mean? An ionic compound, right? Because molecules are for covalently bonded compounds. Formula units are for ionic bonds. So the solubility is for the concentration of formula units, so it's going to be for 1 formula unit, or 1 mole of that substance that dissolves into its individual ions. So if I say I have 1 mole of lead 2 chloride, it dissolves into 1 mole of lead 2 ions and 2 moles of chloride ions. So this is just to recap. This sort of makes it seem confusing, but if I'm going to write this, I'm going to say that this is S, the solubility of it, this is S, the concentration of it, and then this is 2S. So if I told you the concentration of PB, PB's concentration is equal to 2 times the concentration, I'll put that on the outside. 2 times the concentration of Cl minus, right? Which means, likewise, if I give you Cl minus's concentration, that's equal to 1/2 the concentration of Pb plus 2. Do you agree? That's what this is showing you. Pb's concentration is 1/2 that of chloride. They just put the 1/2 in like a different spot. Yes? Does that make sense? Yeah, because if this is S, then this would be 2 times S, essentially.
Lead?
Yeah. Am I writing this the wrong way?
Yeah.
Except I know what I'm saying,
Yeah.
and I'm just not writing it the right way? Yeah. So this is double the concentration of lead. Yeah, I put the 2 in the wrong spot. Sorry. Which means that this is 1/2 the concentration of chloride is equal to lead. All right, so that's why this expression is correct, but you have to just evaluate that it's S and 2S. Sorry about that. Now, did I confuse you?
Yeah.
If I tell you the concentration of lead is 1 molar, what's the concentration of chloride? 2 molar. If I tell you the concentration of chloride is 4 molar, what's the concentration of lead?
2 molar.
Get it? Like you're doing it, it's just, this was just trying to show you how you relate the mole-to-mole ratio. And then you would do it using mole-to-mole ratios too. Like if I gave you the chloride concentration, you could use dimensional analysis and say it's 2 chlorides for 1 Pb plus 2. So there would be your concentration of your lead. It would be 1/2 the chloride concentration. Sorry. So that's true when the solution is saturated. Saturated means that it can't hold any more ions. So once it's reached its max number of ions, then it would continue forming solid. I'm going to write this down because this is super important. When you are asked to find concentration of ions, it will almost always say, find the concentration of the lead ion and the chloride ion, and then find the molar solubility. Molar solubility is simply how much of the solid would dissolve. Molar solubility, I don't know why I can't spell this right now. Molar solubility is going to be S, and this is for the solid. So it's always going to be only 1 S. It's not going to have a coefficient in front of it because we're only ever dissolving 1 mole of a solid. We're not dissolving 2 or 3 moles. We're going to dissolve 1 mole of solid into its individual ions. So molar solubility just means what's the concentration of the solid that can dissolve. It'll just be your S value when it's saturated. So let's try a practice problem. The solubility product constant for lead 2 fluoride is 3.6 times 10 to the negative 8th at 25 degrees C. Write a balanced chemical equation. So they're asking you really to write the dissolution of this, and what do we always start with? Solid. And then we're going to write the equilibrium expression, and we'll keep moving forward. So the first part, if you're not sure, look up here. Otherwise, just do it. Don't forget double way arrows because it's equilibrium. So do you have that? Mm-hmm. All right, next part, write the equilibrium expression. So that's super easy. You're going to make sure you write KSP. And then I'll write it. If you're not sure, look up here. All right, everybody go with that? And then the next part says find the maximum molar concentrations of the ions in solution and the molar solubility of the solution. So again, molar solubility means how much of the solid can dissolve. So watch, when I write out my reactions, I write S, S, 2S. If this were a 3 in front of it, then I would write 3S. I personally always do that because I know that molar solubility means that I'm finding S. And once I solve for S using the KSP expression, I'm just going to go back in and plug in the values to find these concentrations. These S values are the concentrations, right? Because otherwise you might accidentally confuse yourself and plug it back in here and then accidentally square it again. We're not squaring concentrations, right? The concentration of fluoride is just double that of the lead. So now I'm going to solve for the KSP by plugging in 3.6 times 10 to the negative 8 is equal to S. Do you see that? What do I plug in here? 2S because I wrote it. That's why I write things like that for myself so I don't confuse it. And then that's squared. So then what is S times 2S squared? 2 goes into the 2, 2 goes to the S, so this is 4S squared times S, so this is 4S cubed equals 3.6 times 10 to the negative 8th. So when you solve this, you divide by 4, and then you cube root this. So remember that when you cube root it, you're going to plug it in on your calculator as a little hat with a 1/3 in parentheses. So go ahead and try that so that you make sure you don't make a mistake. So the answer is 2.1 times 10 to the negative 3rd. Thumbs?
No. Oh, yeah.
That's S. Okay, but the question asked you to solve for the concentration of the ions, and then it asked you to solve for the molar solubility, right? 3 things you're solving for. You're solving for S, molar solubility. You're solving for the concentration of lead and the concentration of fluoride. So since I solved for S molar solubility is 2.1 times 10 to the negative 3rd. This concentration of Pb plus 2 is 2.1 times 10 to the negative 3rd. And then F is just double that. If you don't write this on the top of your equation, some of you, not all of you, will go and put 2S in here and then square it. I don't know why you'll do that, but you will. So if you take my advice, you're going to put your S's and everything above it before you start. Okay? So the slide here doesn't specifically say the molar solubility. This isn't appropriate to write S equals molar solubility. What you should write is not S equals, you should write molar solubility equals 2.1 times 10 to the negative 3rd molar. Because that's specifically for PbF2. Got it? That's what it means. If I put this much solid in, these are the number of ions that will form. Any questions? All right, a saturated solution. We know this already. A saturated solution, the reason why we're going over it again is because the problems that you're going to see today, problem that you're going to see on your quiz tomorrow, are specifically going to use the word saturated to tell you how to solve a problem. If something is saturated, it means that you can use the KSP value. If it's not saturated, then you can't use the KSP value. You'll have to figure out the concentrations. So just write that down. Saturated solution, that wording means, yes, you can use the KSP value. Now you should know that any K value is temperature dependent. And we know that already because solids will dissolve better or worse depending on temperature, right? Which then in turn would change your K value because your K values, for example here, are always going to be related to the concentration of the ions in the solution. A solution is at equilibrium when it's saturated, meaning it's making solid and making ions all at the same rate. So we saw this slide before, I've talked to you about this. You can figure this out based on radioactive substances, so you can see that it goes into solution and then goes back into the solid. All right, we've gone over this slide. I think this might be like the 5th time I'm discussing it. Right? How does delta S become less than 0? What does that mean? If it's less than 0, it's negative. Is that favorable or not? What is dissolving? Is that favorable? All right, so we assume that dissolving is always positive entropy because you're making ions, but sometimes the overall process of dissolving something can be non-favorable. And the reason why that's non-favorable, we've talked about this before. Think of it like a football player running around a football field and all of a sudden there's all these other players dragging him down. He's not moving as fast anymore, right? So if you're dragging stuff around with you, it slows you down and then everything else slows down. So if I put copper 2 sulfide in water, the copper 2 is a small, highly positive charge, highly meaning it's either a +2, +3, it could be a +4 charge. Highly positive charge The water molecules have their own disorder. The copper 2 ion goes in, which is favorable for entropy, but it starts dragging the water molecules. So they're going around like this, but then all of a sudden now they're attached to it and they're slowly moving around in the solution. So the overall net entropy change is negative because the water molecules slowing down outweighed the positive entropy of the ions being formed in the solution. Make sense? Was that an I don't get it? Right? Dissolving is always favorable. Agreed? So the only way to get an unfavorable entropy is if something else in the solution is gaining order. The water molecules gain order when they start surrounding something else. They're not free to move. Now they're trapped by this positive charge, and they're kind of carrying it around with it in the solution. There's not just one copper ion, too. There's billions of them, and they're trapping all the water from moving around freely.
So how are we going to know when that happens or when it is actually positive? It'll tell us?
It will give you a scenario for sure. It'll say, explain why the delta S of the dissolving of whatever is not favorable. And then you would say, well, dissolving is always a favorable process, therefore it must be a small positive charge ion that is creating order within the water molecules. They always give you the scenario. Remember like intermolecular forces, there were some times where we didn't agree with it, but we still had to explain it? Similar to this. You still would have to explain it. Even though we'd want to say it's favorable entropy, it's non-favorable because there must be order being created in the solution. All right. This is just wrapping in thermodynamics and equilibrium all together. We did this already last section with electrochem. It's all related. So delta G is greater than 0 means it's not favorable, right? It's positive. So I need things to be negative to say that they're favorable. So if something doesn't dissolve, that means that I'm not forming products, which means K is less than 1. Delta G would be positive, right? This is saying that most salts, if we're talking about temperature dependent now, most dissolution of salts is endothermic, which means that they have to absorb heat to become more soluble. We know that. We just looked at the graphs, right? So if most salts are endothermic, and as ionic bonds are normally stronger than ion dipole, that means that the S value becomes negative. Then typically delta G here would become positive, which is true. Where's my marker? Because K is equal to products over reactants. So if K is less than 1, it means that I'm reactant favored, but anytime I have a KSP value, it's always for my solid going to my aqueous ions. So if I'm reactant favored, it means I'm solid favored, which means it's not going to dissolve. Or it'll dissolve at a very, very small amount. All right, take like 30 seconds to just read through this again and understand if this is endo, what sign would this be? If this delta S, what sign would this be? And evaluate how delta G becomes positive. You know this already. Okay? Any questions? Was that a question? No. Okay. So this was going to be positive. This is negative. Positive plus a positive gives you positive. That's what it's saying. All right. How many of you remember Q? What little activity did I do with you to discuss Q? The Cheerios and the Fruit Loops, right? Or the Fruit O's. That were really old. So the point is, at some point, you have to figure out, are you at equilibrium? We did this with reactants and products, but if we're doing it with solubility, all we're saying is, am I at the max concentration that the ions can be held in solution? So if I dump in salt into water, and I dissolve it, can it dissolve more? That's your question. Is it possible that this could dissolve more? How do you know? You measure the concentration of the ions that are there, you calculate a Q value, and then you compare your Q to your K, right? And you're still going to evaluate whether or not Q, keep losing my markers, whether or not Q is greater than or less than K. And all you need to do is just evaluate products over reactants every single time. So if it's product favored, if it's a big number and the numerator is large, it means that you have too many ions because KSP means ions, right? So that would mean that you have too many ions, and if you have too many ions in solution, what's going to happen? You're going to make a solid. So then it would precipitate, right? If you have too few ions in solution and you have too much solid, what's going to happen? It's going to dissolve more to make more ions, because you have to remember that this is the reaction. It's going to ions. All right, so let's evaluate each of these. If Q is equal to K for a saturated solution, then you're at equilibrium. If Q is greater than K, what is too big? A product, right? We just discussed this. If products are too big, look what your products are. They're your ions. So if products are too big, it has to drive back to make reactants. What's your reactant? A solid, so a precipitate will form. If K is less than Q, if Q is less than K, what does that mean? That reactants are too big, right? Because the number is too small. So that means that reactants are too big, so it has to drive to make more products. What are your products? Ions. So it's going to dissolve more to make more ions. Write something down on this slide. Maybe like these things that I just wrote for you. So we're going to look at solving for Q and KSP. No. I'm going to pause again. So this one is picturing what's happening here will be most helpful for you. You have a beaker. I'm going to read the second part to you before we do this part. It says, will a precipitate of lead 2 chloride form when 200 milliliters of sodium chloride with a certain concentration is mixed with 100 milliliters of lead 2 nitrate with a certain concentration? So what's going to be floating around in this beaker? Pb plus 2, Na plus, Cl minus, and NO3 minus. What are my spectator ions? Yeah, so let's not even consider that. I'm going to have Pb plus 2 floating around and Cl minus floating around. The question says, it's basically asking you, do these precipitate? How will they precipitate? Tell me. If what?
Saturated solution.
Yeah, what does it mean if it becomes saturated?
It can't hold any more ions.
So that we've reached the max concentration of ions in solution, right? That's when we will get a PPT, which is essentially it's saturated. That's what saturation means. So what do you think we need to do? Figure out what? The maximum number of ions that could be in the solution. But really the easiest way to go about this is to calculate your KSP and then calculate your Q. And if our Q is less than our K, or if our Q is greater than our K, we'll determine if a precipitate will form, right? And that all is dependent upon the fact that you understand that products over reactants, reactants mean solid, products mean ions. So if I have a Q that's less than K, that means that my what is too big? Reactants would be too big, and it has to continue making more ions. So no, a precipitate won't form. If Q is too big, it means I have too many ions, and then yes, a precipitate will form. So we're going to find K, and then we're going to find Q. So first part says find KSP for a saturated solution of lead 2 chloride if the concentration of chloride is found to be this. Step 1, what do you always have to do? Write the reaction with what? What starts? Solid starting it. Then if you were me, what would you do? Write the S's. I tell you these things because they help. S, S, 2S. Now I'm going to solve for the KSP expression. So you have to look back at the slide and look at what the concentration was. What did they give you? They gave you the concentration of chloride to be 0.0325. But if we look at our reaction, this is equal to 0.0, was it 325? Yeah. That's the concentration. So then what is S? Half that, right? So now you're going to plug that into your KSP expression, and you're going to square that chloride value. So they're writing 0.5, but we know we can just literally put this divided by 2 if we wanted to do that instead. Same thing. Good.
See.
All right, so this is what we're going to compare our Q value to. We're going to compare Q to KSP and determine if it's going to be greater than or less than. So now we're going to go to part B. How do we find Q? You bit your lip? You bit your tongue. All right. Anybody not sure how this came about? We're all there? All right. So now the next part is to find the individual ions. We have to redo our K essentially, but for Q. So this is what I want you to look at, this picture again. How am I going to find the new concentration of this when this was the concentration of it when it first started? What was I got to look it up. What was the concentration of the lead? Nobody knows. Where is it? I see it. Okay. So first, I'm going to write out this reaction so that I can recognize how many ions I'm forming of each of them. So if I were using nitrate, I would have to do double that, right? But this is the concentration of the lead 2 nitrate. This is 2.45 times 10 to the negative 2. What's the concentration of the lead ion? You don't know? Because we write S2S.
Same thing.
Yeah. Anytime that they give you, this is what they're mixing. They're mixing a solid with another solid. So then this is 2.45 times 10 to the negative second. And then we don't care about the nitrate because the nitrate is going to be a spectator ion. Do you agree? But I'm writing out the reaction so that you see it. This is the concentration of it in how many milliliters? In 100 milliliters. My other reaction is the sodium chloride. I make Na plus and Cl minus, and this concentration here is 3.78 times 10 to the negative 2. What's the concentration of sodium? Same thing. What's the concentration of chloride? Same thing, right? But we don't need the chloride because they're spectator and that one's spectator. This is in 200.0 milliliters. Okay. My point to you is that I've mixed them. So what's my new volume?
300.
Can I just take those concentrations and plug them into this equation and see what Q is? I can't because the concentration's not that. That was the concentration of each of the individual solutions and then I mixed them. So when I essentially mixed them, what did I do to them? I think you said it. Diluted them. You heard her.
I got it. I heard Henry.
Henry? So you dilute them, didn't you? You took a 200 and now it's in a 300. You took a 100 and now it's in a 300. There's two ways to do a dilution problem. You can either calculate the moles of PB that are present in the 100 milliliters and then divide by 0.3 total volume, and then find the moles that are in the sodium and then divide that by the total volume, or you can do M1V1 equals M2V2.
Yeah, that just indicates it's expected.
It's up to you, however you want to handle that. So if I'm going to do this, I'm going to say 2.45 times 10 to the negative second molar PB plus 2 is equal to X moles divided by 0.100 liters. Correct?
Wait, so are you doing the other thing?
I'm going to show you how to do it with moles instead of M1V1, but you can choose whatever you want to do. So then you're going to solve for that. How many moles will that be? If you're doing scientific notation, this is 1 times 10 to the negative first. So then you would add them. So that's going to be 2.45 times 10 to the negative third moles of PB plus 2. And now that's in the new volume, which will be 0.300 liters. Do you understand that? I'm going to show you the other way to do it. You can choose. Sometimes it just makes sense to think of something one way for someone and then another way for someone else. So this comes out to 0.0082. 817, I need 3 sig figs. Molarity. But if I used M1V1, I would take 2.45 times 10 to the negative second times V1. What was V1? 100 is equal to M2 divided by my new volume, 300. So 2.45 times 10 to the negative 2 times 100 divided by 300. And I still get 0.00817 molar. So you can do it either way. Both options are fine. Yep.
Why did you write NaCl in there?
Because we have to do that for the next one. I'm mixing two things, and the precipitate that I'm looking to form is lead 2 chloride. So I've just figured out this is the concentration of lead that's going to be sitting in that beaker, right? So now I'm going to find chloride. So you choose which technique you want to use. Maybe you want to do the dilution, M1V1. So sodium chloride was originally 200 milliliters. Now I'm going to find M2, and the V2 is total 300. So this is for sodium at this point. So the concentration here is 0.0252 molar sodium. Everybody okay with that?
What did you get for it?
0.0252. Oh, that's the same thing. I'm sorry.
Oh.
Yeah.
Yeah, let's see too.
0.0252.
I get that.
Why does it not matter? They're all the same thing. There's no coefficients.
Same thing.
All right, so tomorrow we'll finish this by taking each of the concentrations, plugging it into the Q expression, and then comparing Q to K. But this is not on your quiz tomorrow. All right, happy homework. So if you take a picture of what's happening, it's so much better than just trying to figure out step by step. Like, okay, now I do this, now I do that. If you visualize, what we did yesterday is you have in your beaker, you pour in one substance, you pour in the other substance, and now your question is the concentration of Pb plus 2 and is the concentration of Cl minus large enough that I form a solid? And if it's not, then it's not going to form a solid. Agreed? Like the question you just took, that last question on the front page said, here's scenario 1, solid sits at the bottom. Here's scenario 2, I put in more water and solid sits at the bottom. What's the concentration? The same. Because if solid's sitting on the bottom, it means you're holding the max number of ions that possibly could be in the solution, right? So what I want to know from this question is the max number in the beaker? And if it's not, then I'm not going to form a precipitate. So what you need to do is calculate your Q value and then compare it to your KSP value. So yesterday we found out the concentration of the lead ions was 8.17 times 10 to the negative third molar for Pb plus 2. And then the chloride concentration that we had yesterday, I'll just skip through here, was 0.0252. 0.00252. So your KSP expression then for the precipitate is PbCl2 goes to Pb plus 2 plus 2Cl minus. Therefore, your KSP expression is the concentration of Pb plus 2 times the concentration of Cl minus squared. Well, I have this concentration, so I plug it in. I have this concentration, so I plug it in. Right? They're coming from two different sources, so they're not going to match each other. It's not going to be like one is S and the other is 2S. It's just I poured in two different sources of ions. And this is the concentration of one of them, and this is the concentration of the other. So now we calculate and we solve for Q. Here's Q. 5.19 times 10 to the negative 6. So now you have to figure out what does that number mean to me. So I would not suggest memorizing Q's to K's. I would suggest that you recognize that a K always means products over reactants. So if I have a number Q that is less than K, yes. If Q is less than K, what does that mean for this fraction? Does that mean that products are too big? Or does it mean reactants are too big? Reactants are too big. So if the reactants are too big, it's going to push to make more products. I need more products, right? Well, since this is solubility, what's always going to be on the product side? Ions, because what's always on the reactant side? The solid. So if this is going to push to make more ions, it means I need more ions in the solution before this precipitates out. So the question we started with was, does a precipitate form? No, because there's not enough ions in solution. Q was less than KSP, so therefore it's not saturated. You follow that logic? You will do this on free response. I'm going to give you some practice problems for it. You don't get to just look at one problem and be like, ah, yeah, I get it. You really have to try these. These are harder. All right, next type of question. These are equally as hard, but you have to just, again, wrap your head around how you're going to solve this. So here's the scenario before we even read the question. I have a beaker, and inside my beaker, this is true of like any solution. Say you take like lake water or pool water or any source of an aqueous solution, it has stuff in it, right? If it's not pure something, it has other stuff in it. There's ions floating around. Your pool water has ions floating around, right? Then I'm going to pour some other chemical in it, and it's going to precipitate something in that solution. One of those ions will have a lower KSP value and precipitate first, right? Low KSP means low solubility, so it would precipitate first. So if I have a bunch of ions floating around and I'm trying to get a precipitate, why would I want to in like an environmental factor? Why would I want things to precipitate out? To clean them, right? If I want to get stuff out of my water or I want to get something out of the pool, I can throw in some other chemical and then it precipitates out. They do this in pools all the time. And then you have a bunch of solids sitting at the bottom and they vacuum it up and now you don't have that ion in there anymore. So in this scenario, I have two different types of ions. I'm going to pour another ion in, and one of them is going to precipitate first because one of them has a different KSP value, right? So this is my beaker. Inside my beaker, I have floating around calcium nitrate and iron 2 nitrate. What's really floating in the beaker that I'm concerned with? Calcium and iron, right? Why don't I care about the nitrate? Because it's not going to react with anything. What does it mean? Oh, that's +2. What do I mean when it doesn't react with anything? That it has a, what kind of KSP?
I mean, high,
Really, 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 really high KSP, like you're never going to reach it. Does that make sense? Like it still has a KSP value. It's just so high because you can have such a high concentration of nitrate in there that we say it's always soluble. But it does technically have a KSP value. It's just that it would be like 1 × 10⁻40. Do you get what I mean? All right, so we have calcium ions floating around, and we have iron ions floating around, and then it says I pour in slowly sodium hydroxide. So what do I really care about here? Hydroxide. So I pour in the hydroxide. All right, so my choice here is that this is going to happen and form calcium hydroxide, solid, or this is going to happen and I'm going to form iron 2 hydroxide. One of them is going to happen first. Do you agree? Because they have different KSP values. So I could do this. I could calculate Qs and compare and do all that, but what's common to both of these compounds? OH, hydroxide. So if I want to compare them, I really could just say, well, what's the maximum concentration of hydroxide that can be floating in this solution before it precipitates out? This has some sort of max OH concentration, and this has some sort of max OH concentration. Do you understand why I'm saying it has a max? No? Why would the concentrations of these be different? Because they have different what? They have different KSPs. This has a specific KSP, and this has a specific KSP. So the concentration of OH for this compound is going to be different than the concentration for this compound. So really, I can shortcut this and just find what's the maximum concentration of OH that would be allowed in this beaker before it precipitates. And whichever one has the lowest concentration of OH allowable, that one will be reached first and precipitate first. Like I used this analogy a little bit earlier. If this is the max concentration for one of them, 4 glue sticks, and the max concentration for another one is 3 glue sticks, which one am I going to reach first as I start dropping glue sticks into my beaker? That's it. It's as simple as that. You're trying to figure out which one is the lowest, and that's the one you're going to reach first. Make sense? So let's do it. It gives us enough information to figure that out. So I have KSP for this, and I have KSP for this. So what is this going to be equal to? According to this reaction, it's going to be equal to Ca plus 2 times OH concentration squared, right? But I don't know the OH concentration. I'm not going to just double it. I'm not going to do that. I'm just going to figure out what the OH concentration is. What's the concentration of calcium already in the beaker? Look at the question. 0.14. So isn't this easy now? I can solve for what this number should be. And then this one is going to be the concentration of Fe plus 3, 2, sorry, I keep writing the wrong thing, times OH minus squared. And I have this concentration, 0.25. How do I just know it's 0.25? Because originally I figured out that the ions in there are in a 1-to-1 ratio for the Fe and the FeNO3. Nitrate would be in a 2-to-1 ratio, agreed? So I'm skipping writing all that out because I assume that you recognize that. Do you? Okay. So now I'm just going to plug those numbers in. So let's go to the next slide so that you can see the math clearly written out. So that's what I just wrote out here, is that it was equal to calcium's concentration times OH minus concentration squared. I plug in for the KSP, and then I do some algebra, and I solve, and I get 7.6 times 10 to the negative third molar. This is of OH minus for the calcium hydroxide solid. All right, so we have some value of hydroxide, and then I'm going to look at it for iron. And then we're going to think about it like glue sticks. Which one am I going to reach first? Right, we're going to figure out the other one. Writing it down, are you done?
No.
Okay. A minute. Okay, so we get this value for calcium hydroxide, so now let's check the hydroxide in iron 2 hydroxide. So now I have 2.5 times 10 to the negative 7th molar. Go ahead and jot that all down, and then we'll talk about comparing them. So now let's compare the two values. So we have 2.5 times 10 to the negative 7, and then we have 7.6 times 10 to the negative third. Which one's smaller? The negative 7, right? Sometimes our brains don't function very well when we think of negative exponents, so really think about it. But the 2.5 times 10 to the negative 7th is smaller, so we'll reach that one first. So that one's going to precipitate first, right? And then guess what? Once all of those ions are precipitated out, what was that for? Iron. Once all the iron atoms go away and they all precipitate to iron hydroxide, and if there's still a surplus of hydroxide coming in, what would you think would happen next? It's going to start precipitating the other one. Good. Right? Like in an environmental sense or in any sort of chemical sense, you might have to evaluate that and say, all right, well, I don't really care about that first precipitate. I just know that I have to finish precipitating that first and then keep adding more to get the other one to precipitate. That's an option too. Like on the quiz you just took, maybe you precipitate the black one first, you remove all the black precipitate, and then you start precipitating the yellow one, right? Because the black precipitate is less soluble, hence it precipitated. Mind's blown? All right, we already did this slide, so I'm not going to go back over it with you. Common ion for chloride? Common ion for chloride, yes? And then this is just some further common ion and Le Chatillier's and how it shifts, okay? Okay. Gas solubility. We're done with all the math. Look. Shh. Those problems are really challenging. So when I give you the practice problems, you really need to try them and then check your answers on the back to make sure you understand them. The rest of these slides are just sort of theory stuff that you probably know. We just want to make sure you understand it. So most gases are less soluble as you heat them up. So typically we say solids are more soluble when we heat them up, right? More solid dissolves into liquid. But when you have an aqueous solution and you dissolve gas into it, how does a substance go from a liquid to a gas in the first place? What do you have to do? Add heat. So if I heat a sample up that has gas dissolved in an aqueous solution, what's going to happen to those gases that are dissolved? They're going to go back into the gas phase, right? So if you increase the temperature of an aqueous solution with dissolved gases, those dissolved gases will go back into the gas phase very easily, because think of kinetic molecular theory and those intermolecular forces. Gases typically have weak intermolecular forces. They're typically just London dispersion. There are not that many electrons in them, so they're low polarizability. And so they have weak intermolecular forces, so as you increase temperature, kinetic energy increases, it severs their intermolecular forces, and they go into the gas phase, right? If gases are typically nonpolar, then what force of attraction allows them to be dissolved in water? We went over this already. Ion-induced dipole, is that what you said? Ion? They're not, there's no ions. Dipole-induced dipole. Yeah, so the gases go into water. So that's what all of this is saying. As kinetic energy increases, they break free, they sever their intermolecular forces, and they go into the gas phase. All right, you've seen this before. This is the fisherman, one who studies chem and one who doesn't study chem.
I drew this picture on one of my things last year.
You should have. It's a great idea. Someone else actually in block 2 is just discussing how ice fishing actually is pretty effective also, and how that would make sense. So we can talk about that a little bit. But so why is the person who's not studying chemistry not catching fish?
Fish want more oxygen.
The fish need more oxygen. And where do the fish go on a hot sunny day? Okay, what happens on the surface of the water?
Gets warm.
It gets warm. And the oxygen's particles are, now I'm saying ion, are induced dipole-dipole, and they're weak, and then they start heating and kinetic energy increases, and then they release the gases into the atmosphere again. So there's very little oxygen gas on the surface, right? And then as you go deeper, it's colder. You know that from swimming. So that part of the lake can hold more oxygen, so the fish stay at the bottom on a hot, sunny day, right? This is similar. It's almost like just inverting a pot of water. The heat source is on the bottom of a pot, right? So you start seeing those little gas bubbles coming from the bottom and escaping from the top, because they are trying to escape as their kinetic energy increases. This is just that the heat source is on the top, so it's escaping, the gases are escaping from the surface. So you catch fish on the bottom, you don't catch fish on the top. That's about it.
So happy though. Yeah.
All right, so this is just another explanation about gases and heat. So warm carbonated drinks go flat faster than cold. A carbonated drink like soda. So you have gas, carbon dioxide gas dissolved in the soda, and then as it's heated, it begins to go back out into the atmosphere. How many of you have had a cooler full of soda for a party or something like that, and then you don't clean up for days and days, and it's the summer, and you open it back up, and you're like, oh, let me get one of these. What's wrong with it? Probably a few things. It's flat, and what does it look like? Did you say something else?
Moldy?
Moldy?
Soda? You get
It's in a can of soda.
moldy soda.
What happens to your can? Did you ever experience this?
Doesn't it? No, it pops up.
It pops up. You get like a dome, and the whole thing starts getting larger, and if you continue to heat it, what's going to eventually happen? It's going to explode. Alexa's experienced this. Her cans of soda in the cooler literally look like a big, like, I don't know, cylindrical ballish thing. Because what happens when it heats up outside and it's not in the cold water anymore? The gas escapes. And where is it going to go? It's a sealed container. So it just expands the container and expands the container until it can't expand anymore. And if you continued heating it, it would explode, right? Because it doesn't have an outlet for that gas to escape. So this is sort of what it's saying too. Thermal pollution. All right, this happens especially for like nuclear reactors. Nuclear reactors are always built by
Say that again.
nuclear.
Nuclear.
It's nuclear. There's no U in
Not
it. She said
nuclear.
nuclear.
There's a U in nuclear.
Yeah, but it's
That's not
where's the
Anyway,
U?
we're moving on.
Nuclear.
So they're usually built near lakes and rivers. Hey, back there. Shh. That table, man, they're gonna need to become an island. That means you have to sit by yourself in an island.
I'm gonna end up sitting at your desk.
All right. So what happens if you're a nuclear reactor and you go near a lake or river? What do they use to cool them down? Do you know? They like literally plumb water from the lake and the river, and then they have it kind of funneling around whatever system they have. I've not been to a facility like this, but this is what I've been told. To cool it down, they need a lot of water, so they use it directly from the lake or the river. So it's used to cool something down. We know thermodynamics, you can't exchange cold, you can only exchange heat. So the heat from the reactor goes into the water, and then where does the water go back? Into the lake or river. So what happens to the fish? They die.
Wait.
You are something else. All right, that's what this is saying. So there's all sorts of environmental implications. So this is the last part, Henry's Law. All this is just basically Henry's Law says that the solubility of a gas is directly related to its pressure. So guys, you're not paying attention. Stop. You can have gas solubility is definitely dependent upon temperature, but it's also dependent upon pressure. So I can push gases into aqueous solutions. I can do it by pressurizing the system, like soda is a pressurized system when they first dissolve the gas. And then we'll talk about another way, another example of that. But the greater the pressure is on the surface, the more gas dissolves into that aqueous solution. So even if I had a cup of water out right now, whatever gases there are floating around in our room would be dissolved into my water because there's a certain atmospheric pressure that's pushing them down. If the atmospheric pressure in here rose very rapidly, then there would be more dissolved gas particles in my water. So that's what this is showing. I have a certain number of gas particles in the aqueous phase, and then I pressurize it, I push them down, and then they actually go into the aqueous phase. So I have a higher concentration of gas particles in the aqueous phase than I would in that gas phase when the pressure is high. So this is how soda is made. It's showing you that they pressurize that little spot up there. So it keeps it under pressure, which means that you have lots of carbon dioxide dissolved into it. And then once it opens, that little sound is the gas escaping immediately. And over time, it's going to escape until the pressure of the bottle, of those gases, is equal to the atmospheric pressure. And so the concentration of the CO2 gas that's dissolved goes down tremendously until it reaches atmospheric pressure. Gas solubility and pressure, again, is showing you that as you increase the pressure, the solubility of the gases increase. But let's talk about each of these. Why does hydrogen gas have lower solubility at the same temperature and pressure, than NO? So it's solubility in water. That's the key thing. These are all non-polar. This one is slightly polar, right? Non-polar, non-polar. So the polar one experiences what with water? What kind of forces? Dipole, dipole. It's polar and water is polar. So dipole, dipole means that you are going to get stronger forces of attraction. So it's going to dissolve better as you increase the pressure. These are both nonpolar, so this is dipole-induced dipole. But why is O2 going to be dissolved better in water? More electrons, so it's more polarizable. Okay? Which somebody asked in block 2, can I make soda with other gases? And the answer would be yes, except that you wouldn't get as much CO2, you wouldn't get as much gas dissolved as you do CO2, because CO2, again, is nonpolar, but it has a lot of electrons, compared to making soda with nitrogen gas. You're not going to get as much dissolved in your soda to make it bubbly. All right, the last 2 slides here, we have to go quickly. You might have heard of the bends. The bends is when a scuba diver goes down to the bottom of the ocean. They're breathing in a tank. I have to go quickly because we have to go over midterms. But they're breathing in a tank of air. Air is mixed with oxygen and nitrogen. So when they go down, They literally swim deeper and deeper. The pressure of the ocean is literally just weighing on their body. And so the gases, because when pressure increases, gases are greater solubility. The nitrogen gas dissolves in their blood into aqueous nitrogen, just like oxygen does. But if you ascend too quickly to the surface, that aqueous doesn't redissolve back out of your blood. And it bubbles, it gets trapped into your vessels and your capillaries as you're heading back up to the surface. It gets trapped as now a gaseous bubble, and then it travels through your bloodstream, and if it travels to your brain, it could kill you. Or it could just make you really nauseous and sick, and they have to repressurize you into a pressurized chamber and do all this stuff. So some scuba divers, which I have no idea because I've only been scuba diving once, use helium in their tanks mixed with oxygen because helium is less polarizable, so it doesn't dissolve as readily as nitrogen would. So I'd imagine that they would come up from the surface and everybody would have high-pitched voices as they're talking to each other. That would make sense since it's a science explanation.